Numerical Laplace transform inversion and selected applications. Patrick O'Cano, Ph.D. March 5, 2010. Outline. The talk is organized as follows. Basic definitions and analytic inversion. Issues in numerical Laplace transform inversion. Introduce three of the most commonly known numerical inversion procedures. Dolbett's method. Week's method. Post's formula. Illustrate through applications. Pulse propagation in dispersive materials. Calculation of the matrix exponential. Future directions and conclusions. Overview. Contributions. Laplace transform definition. A Laplace transform is a tool to make a difficult problem into a simpler one. Difficult time-dependent problem. Solve simpler. Laplace space problem. Time-dependent solution. Laplace transform solution methods are a standard of mathematics, physics, and engineering undergraduate education. Laplace transform definitions. A sufficient existence condition is that f(t) be piecewise continuous for non-negative values of t of exponential order. Intuitively, the Laplace transform can be viewed as the continuous analog to a power series. Laplace transform inversion. How does one return from the Laplace space representation to the time domain? Richard Bellman. We can alleviate some of the suspense at the very beginning by cheerfully confessing that there is no single answer to this question. Instead, there are many particular methods geared to appropriate situations. This is the usual situation in mathematics and science and, hardly necessary to add, a very fortunate situation for the Brotherhood, analytic inversion. The analytic inversion of the Laplace transform is a well-known application of the theory of complex variables. For isolated singularities, the Bromwich contour is the standard approach. Real. Sigma. Abscissa of convergence. Isolated singularities. Imaginary. Laplace transform inversion is not a unique operation. In practice, one can assume that the analytic inverse is well defined. Lerck's theorem. Numerical inversion issues. The numerical inversion of the Laplace transform is an inherently ill-posed problem. To combat these numerical issues, one may use two tactics. Fixed-point high-precision variables. Use of multiple algorithms, each with efficacy for certain classes of functions. Inherent sensitivity due to the multiplication by an exponential function of time. Algorithmic and finite precision errors can lead to exponential divergence of numerical solutions. Fixed-point high-precision variables. High-precision variables are required for most inversion methods. This requirement is important consequences. Numerical LT methods are typically slower than other time propagation methods. Implementation requires either an environment where high-precision variables are innate, additional high-precision variable software packages, Sigma, double precision, 10308 10308. 10380 709. Large for even modest times. Mathematica. Aprec. An arbitrary precision computation package. Lawrence Berkeley National Laboratory. D. Bailey, Y. Hyder, X. Lee, B. Thompson. GMP. GNU Multiple Precision Arithmetic Library. MP. MATLAB-based toolbox. Ben Barrows. MATLAB's file exchange. Numerical inversion time Laplace 1749 to 1827 Heaviside 1850 to 1925 Post 1930 Weeks 1966 Fourier Series 1968 Talbot, 1979. Euler, 1707 to 1783. Post's formula, alternative to integration, arises from Laplace's method. Post, 1930, Gaver, 1966, Valko-Abate, 2004. The Weeks method. Laguerre polynomial expansion. Ward, 1954, Weeks, 1966, Weidmann, 1999. Fourier series expansion. Fourier-related method. Koizumi, 1935, Dubno-Abate, 1968, De Hoognight-Stokes, 1982, De Moray, 1999. Talbot's method. Deformed contour method. Talbot, 1979, Weidmann and Trefethen, 2007. Talbot's method, 1979. Talbot's method is based on a deformation of the Bromwich contour. The idea is to replace the contour with one which opens towards the negative real axis. Talbot's method requires that. Talbot's method. The method is easily implemented in Mathematica. Precision. Run time 10. 0.047. 20. 0.141. 40. 0.391. 80. 1.625. The Talbot method answers are accurate up to the computation precision for time t equals 1. Time eval equals 1. Val equals half. Flap s underscore equals exp minus 2 sqrts. Fun exact t underscore equals exp1 slash t slash sqrt by ttt. Val exact equals and fun exact time eval 1000. Stalbot r underscore comma a underscore equals r cot a plus ira. Dzdo r underscore comma a underscore equals ir 1 plus a plus cot a cot a minus 1. Timed fun r underscore comma t underscore equals 1 slash 2 pi I. Nintegrate exp stalbot r a t flap stalbot r a dzdo r a pi. Working precision registered 20. Time eval, approxival equals timing timed funval, time eval. Rel error equals abs approxival val exact slash val exact. Talbot's method. The primarily difficulty lies in the selection of appropriate values for the contour's parameters. Mathematica's adaptive integration fails for the same parameter values. Attempts have been made to automate the selection. Algorithm 682, Talbot's method of the Laplace inversion problems, Murley and Rizzardi, 1990. Fortran. This is an active area of research. Optimizing Talbot's contours for the inversion of the Laplace transform, A. Weidmann, 2006. Parabolic and hyperbolic contours for computing the Bromwich integral, A. Weidmann and L. N. Trefethen, 2007. Post's formula, 1930. Emil Post's inversion procedure provides an alternative to Bromwich contour integration. There are two features of Post's formula which are particularly attractive. It contains no parameters, save the order of the derivative and the precision of the computations. The inversion is performed using only real values for s, without priority knowledge of poles. Post's formula manifests the same inherent ill-posedness from which all numerical inversion procedures suffer. Errors are amplified. Multiplicative factor grows quickly with the order of the derivative q. The method converges slowly. One needs an expression or approximation for the higher-order derivatives of f's. Derivation. Post's formula can be derived using Laplace's method. Approximate derivatives. Finite difference is an obvious method by which to approximate the derivatives of a reasonably behaved function. The Gaver functionals can be computed by a recursive algorithm. Gaver Post formula. 1966. Derivatives. Post's formula does not require a finite difference approximation. For a particular function form, for example composition of two functions, a tailored method may be more robust. Faraday-Bruno's formula. Bell polynomials of the second kind. www.mathworks.com/matlabcentral/file-exchange/14483. Acceleration. Sequence acceleration methods be used to greatly increase accuracy. The proper application of an acceleration convergence method requires some additional knowledge about the series. Post's formula is logarithmically convergent. Slow sequence, FQT. Linear or nonlinear. Transform. Fast sequence, HQT. Gaver, 1966. Acceleration. Win-Row algorithm is well suited to logarithmically convergent sequences. Studies have shown that it is useful for the Post formula. Nsham in Mathematica implements these acceleration methods. Post inversion formula and sequence acceleration. UA Vigor Project 2009. J. Kane and B. Berman. Application of Post's formula. NSF Grant ITR 0325097. An integrated simulation environment for high-resolution computational methods in electromagnetics with biomedical applications. Moisey Brio, et al. Rapid computation of the distribution of an initial optical pulse in a fixed dielectric medium with a non-trivial material dispersion relation. Input pulse of light, out pulse of a different shape. Biological materials often have a dielectric constant, which is a complex function of wavelength. Create databases of pre-computed tables which can be used by devices which must operate in real time. Cold-type dispersion relation. Many real-world materials can be described by a cold-type dispersion model. Brain white matter. Fractional A. Coefficients. A standard method used in computational optics is to incorporate the dispersion relation by means of an associated difference equation. For fractional coefficients, it is not clear how to translate into an associated equation. Maxwell's equations. Maxwell's equations are the starting point for this analysis. In the Laplace space, the convolution and derivatives become multiplications. Temporal convolution. Maxwell's equations now have a simpler form. Eliminating the magnetic field H from the problem, one obtains the wave equation in Laplace space, Maxwell's equations. One can more succinctly state this last equation as applying a Fourier transform yields the desired solution in the joint space. Database coefficients in the joint space. The solution in a dielectric medium can be characterized by one coefficient alpha and its time derivative. Compute high-order derivatives of alpha, k, s, and beta, k, s. Beta derivatives are trivially obtained from the alpha derivatives. For a given dispersion relation epsilon rs, the coefficients are pre-computed and stored in a matrix of k versus time. The crux of the problem is the arbitrary precision calculation of the qth derivative of alpha. Derivative approaches. Standard Gaver Win-Row. Finite differences plus Win-Row acceleration. A brute force application entails a computation for each k and s. Gaver Post. The arbitrary precision computation of the dispersion relation epsilon rs is time-consuming. Dispersion relation is independent of k. More efficient to store epsilon rs and call for each k evaluation of alpha. Bell Post. Analytic derivatives plus Win-Row acceleration. Store epsilon rs and its derivatives. Use Faraday-Bruno's formula for the qth derivative of the computation of two functions, Bell Post method. The problem of determining the time dependence of alpha, k, t, and thus the electric field is reduced to evaluating the susceptibility function and its arbitrary order derivatives. Cold-type dispersion relation. For white brain matter, the derivatives of epsilon Rs can be found by using the Faraday-Bruno formula. Mathematic implementation flow diagram. Inputs. Choose Qmin, Qmax. Inversion time t. Take an explicit expression for epsilon Rs and its derivatives. A set of wave number k. Evaluate epsilon Rs and its derivatives at s equals q/t. Compute S2 epsilon Rs and its derivatives via Leibniz's rule. Compute the Bell polynomials from the recursion relation. For k, compute S2 epsilon Rs plus C2K2. Repeat for each q. Compute the Qth and Q1th derivatives of alpha, k, s. Compute the Qth derivative of beta, k, s. Approximate the inversion coefficients via Post's formula. Apply Win-Roe acceleration. Brain white matter, run time. Case. Log A. P. Bell post. Minus 0.592. 1.670. Gave a post. Minus 0.189. 1.438. Brute. Gave a. 0.148. 1.655. Time equals 16/3 t0. 100 digits precision. The Bell post and Gave a post methods are faster than a standard Gave a. The acceleration dominates over the sequence computation times. The time follows a polynomial growth with Qmax. Brain white matter, accuracy. Time equals 16/3 t0. 100 digits precision. The Bell post and Gave a post methods have comparable accuracy. At higher precision. And post-formula derivative orders, the Weeks method, 1966. The Weeks method is one of the most well-known algorithms for the numerical inversion of a scalar Laplace space function. Its popularity is due, in part, to the fact that it returns an explicit expression for the time domain function. The Weeks method assumes that a smooth time domain function of bounded exponential growth can be expressed as the limit of an expansion in scalar Laguerre polynomials. The coefficients, an, contain the information particular to the Laplace space function. May be complex scalar, vectors, or matrices. Time independent. The Weeks method. Two free scaling parameters sigma and b must be selected according to the constraints that b greater than 0 ensures that the Laguerre polynomials are well behaved for large t. Sigmas greater than sigma 0 abscissa of convergence. Laguerre polynomials. The Weeks method. The computation of the coefficients begins with a Bromwich integration in the complex plane. Assume the expansion. Equate the two expressions, key Weeks method facts. It is known that the weighted Laguerre coefficients have the Fourier representation. Performing the appropriate substitution. Assuming it is possible to interchange the sum and integral. Equating integrands leaves Mobius transformation. One may apply a transformation from complex variable S to a new complex variable W. Isolated singularities of F's in the S half-plane are mapped to the exterior of the unit circle in the W-plane. W-plane representation. With the change of variables, one obtains a power series in W, whose radius of convergence is greater than 1. The function is analytic on the unit circle. Numerically, the evaluation of the integral can be computed very accurately using the midpoint rule. Matrix exponential application. An application of the Weeks method is to the calculation of the matrix exponential. What does it mean, the exponential of a matrix? Why don't we just calculate this? 19 dubious ways to compute the exponential of a matrix. Siam Review 20, C. B. Moeller and C. F. Van Loan, 1978. 19 dubious ways to compute the exponential of a matrix. 25 years later, Siam Review 45, C. B. Moeller and C. F. Van Loan, 2003. Inverse Laplace transform, number 12. Apply the Weeks method. Resolvent matrix of A. Matrix exponential application. MATLAB, paid approximation with scaling and squaring, number 3. MATLAB demos. Exp Demo 1, paid plus scaling plus squaring in an M file. Exp Demo 2, Taylor series. Exp Demo 3, similarity transformation. Exp beam propagation equation. Non-paraxial scalar beam propagation equation. Discretization in space yields a set of odes. The Laplace transform in Z yields U equals a component of the electric field. Beam propagation equation. The Laplace space function is of a matrix exponential. The issue is how to pick the Laguerre polynomial parameters sigma and b. Weeks' original suggestions. Error estimate motivated approach. Weidmann method. Minimization of the error estimate as a function of sigma and b. Minute max method. Maximum the radius of convergence as a function of sigma and b. Expensive matrix inversions. Midpoint rule on circular contour. Error estimates. A straightforward error estimate yields 3 contributions. Discretization error, finite integral sampling. Truncations error, finite number of Laguerre polynomials. Round-off error, finite computation precision. Midpoint rule on circular contour. Weidmann method. Truncation. Round-off. Minute max method, beam propagation equation example. Multimode interference coupler. Sigma. B. Maximum. Solution. Absolute error. Weeks. 1. 32. 12.28. Minute max. 20. 10. 0.00119. Weidmann. 11.84. 16.79. 0.000425. By proper selection of the parameters, it is possible to perform the calculations in double precision. Pathological matrices. An application is the exponential of special matrices. www.math.arizona.ed/brio/weeks_method_page/pcano weeks-method.html. Weeks. Min-max. 2 search methods. Weidmann. Gallery pay, 6. 211111. 121111. 112111. 111211. 111121. 111112. 6x6 pay matrix. Maximum element relative error. 32 coefficients. Eigenvalues. 1. N plus 1, 7. Future directions December 2009. NSF proposal submitted. LAP-CL, robust parallel numerical Laplace transform inversion via a Secuda library and application to optical pulse propagation. Mosey Brio, University of Arizona. Patrick Kano, Applied Energetics Incorporated. Paul Dustert, Coker College. Extend NSF supported posts formula work to 2D and 3D. Tables of coefficients for multiple dispersive materials. Mathematica is too slow. CUDA. NVIDIA's Compute Unified Device Architecture. NLAP requires multiple simple arithmetic computations in high precision. MATLAB CMEX files. MATLAB. NLAP. Front end. Summary and conclusions. The purpose of the presentation was to provide some insight and illustrate applications of numerical Laplace transform inversion. Standard methods. Dolbett's method. Post's formula. The Weeks method. Illustrated 2 examples. Calculation of the matrix exponential. Optical pulse propagation in dispersive media. Numerical Laplace transform inversion is a topic. Multitude of nuances to provide avenues for further research. Popularity increase as computing power improves. Potential for practical application in diverse fields. Great utility and intellectual merit to the development of a general numerical Laplace inversion toolbox. Sources. Numerical inversion of the Laplace transform, Bellman, Calabar, Lockett, 1966. Peter Valco's NLAP website, www.p.camu.edu/valco/public%5fhtml/nil/ Numerical inversion of Laplace transforms using Laguerre functions, W. Weeks, Journal of the ACM, Volume 13, No. 3, pp.419-429, July 1966. The Accurate Numerical Inversion of Laplace Transforms, James. Math. Apple, Volume 23, 1979. Application of Weeks' method for the numerical inversion of the Laplace transform the matrix exponential, P. Kano, Embryo, J. Maloney, Com. Math. Sci. 2005. Application of Post's formula to optical pulse propagation in dispersive media, P. Kano, Embryo, Computers and Mathematics with Applications, 2009, Backups. Backup. Laguerre polynomials. An unstable approach to obtain the time domain function is to generate the Laguerre polynomials is to use the recurrence relation. A backward Clenshaw algorithm is a stable method. Analytic inversion. Application of Post's formula. Post's formula was implemented to invert the Fourier-Laplace space coefficients, which arise from the solution of the optical dispersive wave equation. We considered 3 implementations. Standard gave a Win-Row, gave a Post, Bell Post.